This is the first time I'll learn about a lot of chip design.
Chips are the ones that drives the whole world. 5 million transistors on a single chip. And if you see, there are small tiny capacitors on the board also. So by the way, Edge AI has got a lot of demand right now in the market, and industry is looking for candidates who can build Edge AI applications on hardware. The demand for semiconductor engineers is going to rapidly increase by 2030, 2032.
I can imagine.
Yeah, and we need a different kind of engineers.
Hi, today we have Kunal Ghosh, founder of VLSI System Design, VSD. VSD has made its own chips, educational development boards. We have some today. VSD teaches VLSI System Design to people of all ages, skills. Hi Kunal, thank you for coming to this talk. This is the first time I'll learn about a lot of chip design. I could have done it in the lift when I meet you.
Right.
But this is a better setting.
Yeah, thank you for inviting.
All right. I want to sort of learn about your journey, entering college, first job. You've done, this is the startup that you're doing.
Right.
How did you start VSD?
Okay.
Tell me about that first.
Okay, so my dad is from Reliance Infocom.
Mm-hmm.
He was general manager in Reliance Infocom, and during my schools and colleges vacations, he used to take me to all this Infocom setups and all, where we had a lot of big screens, systems, technology, all tech.
Did you go to Knox or something?
I went to Knox. Yeah,
Okay.
I went to Knox. I did my internship over there for the CDMA technologies, building BSs, base stations for those. So that is my background, and from there the interest to tech actually got evolved. While doing my research about what actually drives the whole, let's say, Infocom. The chips word came very frequently in our minds, and there was a subject in our semester 5 or 6 under chip design. It was called VLSI chip design. So that is what interested the whole thing. Then a little bit of deep research got to a point which said that okay, this is what drives the whole world. The chips are the ones that drives the whole world. So that's how we started looking for a master's program in chip design. And there were top institutes, so we have to go through GATE exams and all. Luckily, IIT Bombay was the only institute that got me over there. So my rank wasn't that great. It was in 2000s. But IIT Bombay had a special program called as Project Research Assistant. So the way it works is there are top rankers who take the top seats, but there is a category of projects in IIT Bombay where they look for people who actually can work and earn, like a work and earn. So there they interview among their, I think 1,000 students apply all over India to that particular program, and it was specifically for chip design, nanotechnology. It was called as nanotechnology program. So there they had interviewed close to 1,500 participants, and they selected only 5. And the 5 participants, 5 students were the ones who could drive projects, who could do work, and parallelly they can run their courses. We had some course programs over there. So that was the kind of skill that they were looking forward for. So that's where I entered VLSI, and what I do currently, that is not my core area. My core area in masters was into semiconductor manufacturing. So in semiconductor there are two domains. One is the manufacturing, which actually manufacturing chips, and one is the design, which is very popular in India. So mine was into manufacturing, and manufacturing deals with a lot of physics and mathematics. So my background is physics and mathematics, semiconductor device physics and mathematics. So that's where we learned a lot about semiconductor manufacturing, and but unfortunately in those days, 2008, 9, 10, there was not much of manufacturing jobs in India. So while I was specializing in manufacturing, I had to do a special course on the design side in semiconductor design. So additional thing I did along with my masters, and that's what got into semiconductor design. From there, my first job was in Qualcomm. In 2010, I got placed in Qualcomm.
Yeah.
But there was an idea that was going on within the college that how unstructured the whole thing is and how unstructured the entire system for getting into a VLSI. While I was preparing for my semiconductor job, it was I had to go through a lot of things. It was not very well structured even in the online part. That's where I talked to my professor at IIT Bombay, and he came up with some sort of ideas and how do we basically structurize the whole thing, start from the first principle.
Yeah.
And being into design and being into manufacturing, both I've seen the best of both worlds. That gave me access to the entire spectrum, the manufacturing, design, and how do you do the whole thing.
You're the full stack chip
The
design.
full stack, and plus my school and college background of doing CDMA systems in Reliance Infocom, that also helped us a lot. The whole stack was very much, the clarity was very much there as a part of what do we want to do as a part of this company.
Got it.
That's when we started 2011, me and along with my co-founder Kunal Ghosh, we both started this company into edtech space. It was mostly into edtech. So we were not a training company. We started with the mindset of an edtech company, that the idea was to help as many institutions across India or globally as possible to use our technology to enable structured learning across India and across the globe.
You didn't want to run programs. You wanted to enable others.
We want to enable the technology. But when we started with the idea of creating the technology, we found that the curriculum itself, it was a little bit, it was not aligned with the current industry trends, because industry wanted something and the curriculum ended at something else. So that wasn't ready. So we started from scratch again. We built our own curriculums. We built our own what is relevant in the industry. We started with that. The second problem that the roadblock that we hit was the tools, the softwares to build chips. That's pretty expensive. I mean, you have to pay huge number to get access to the EDA. Over here we call it as EDA tools, electronic design automation tools. So we call it automation tools or CAD tools, CAD tools. So these are very expensive tools. So the best way, again, we started to research around, what will be the best way to make the programs high quality, low pricing, and it should be reached to the customers very fast. So that's where the concept of open source came into the domain. So the way Red Hat is a company, the way Red Hat grown, we studied little bit of the founder psychology behind opening the Red Hat company. So he basically took up the founder, the company. He took all the open source stack available. He built a wrapper around it, and that was basically sold at a fee. That was a very good model for the software domain. So we took that idea and somewhat packaged the whole hardware stack around. We packaged the whole hardware open source stack and branded it as VSD, as our company, and we started selling that at a very low fee. If the fee was, at that point of time, it was $10, 600 rupees, 700 rupees in that price range, and we flooded the market with that concept, and people liked it. And there were a lot of people, and I'm talking about 2012, 2013, when online was not very popular. That time online became popular right now. So that time online was not very popular, and we were the only ones who was doing online edtech kind of thing, because we wanted to keep the cost low and quality high, and we want to deliver it to the customers very fast. So with that principle, that was the first time when we launched that first edtech solution. And since then, the trend has become very popular. Since then COVID hit, and when the COVID actually hit, people found a value of this ecosystem of online thing, and that's how things became popular. Then we in 2018-19 IIT Madras funded one of our open source projects with them. So we went to Chennai. We stayed there for about 11 months. We finished the project over there. Came back to Bangalore. Then post COVID, then there were a lot of opportunities from Google and company. There is one more company called eFabless to build chips using open source EDA tools. And since we already had that entire background, we got an entire funding for manufacturing chips for a couple of our students. 2021, 2022 is the time where we actually got our own chips built by the student community. So this was not very popular. A college student, third year, fourth year, building chips as a part of his as a part of his journey. That was not very popular, and that was not very too much known to the at least in the tier 2, tier 3 cities. It was a trend in tier 1, like IITs and all. We used to do chips, but in tier 2, tier 3, building chips, manufacturing it, taping it, manufacturing, getting the chips back, and making sure the chips are working. I'll show you one of the boards. Making sure the chips are actually working. That was not a very popular trend. So that trend was brought over here, and at scale. That's very important, because things has to be done at a larger volume, and it has to be very effective, high quality. So that wasn't there, and that's what we brought in partnership with Google and eFabless. So they funded close to our 67 projects was actually funded by them. And fortunately, almost all the chips that came back, they were all working fine. And students and the chips whom they belong to, they actually carried the board and the working chips with them in their interview and saying that this is what I've built. That's how they basically got that. So the trend became very popular. And now I think everybody is, most of the government agencies and the Indian Semiconductor Mission, which is a part of this whole, they're all following this particular trend. So that has been an entire journey from school till, so it all started from the schools, and then it went to colleges, then in the system, and now independently the company has been working for the last 14 years.
Yeah. I remember discussing. Okay, so I don't know tape outs and wafers. I've only heard the term, so you can probably teach us that.
I'll teach you.
But I remember a quick discussion with you earlier, I think a couple of years ago, when the first board came out, that you chose RISC over CISC. I don't even know if that's how they're pronounced.
Yes.
Are you still sticking to that decision? Why that decision?
Okay.
Is it better for people to learn using that way?
So now there is a little bit of history over there. There are other technologies. There are other proprietary technologies, and RISC. So one which we use, that's a 5th generation of RISC.
Okay.
The advantage of that is, so all your systems over here that you see over here, they run on some architectures, and the laptops and all of it, they use an architecture which is proprietary. You can't you basically companies license the architecture.
Okay.
And the license cost is it goes to huge numbers. RISC-V was the technology that was actually initiated by Berkeley, University of Berkeley. From University of Berkeley, it came to IIT Madras, and we got a hang of it. And once we started exploring it more, we built an idea around it, saying that if this is a technology which you can actually see it, you can actually, like, kind of open source. It's an open source technology. You can see the technology, you can customize the technology, you can build something on top of it. You can build your own patch, add another architecture, and you can build your own customized architecture. So these all things are possible using a RISC-V architecture, not the previous generations of RISC or RISC. So that actually opens up a lot of possibilities. Now, right now, if you look into the other chips, you cannot see what is there inside the chip. But what is possible with the RISC-V technology, you can see the entire hardware from scratch in a text format. So
is it? I didn't know that.
So basically, you have an architecture and you build a hardware that implements that architecture.
Okay.
You are allowed to see that particular hardware and the architecture in conjunction, and you can build things on top of that. So now, instead of just learning things, now students or all the community, they are doing something called as product-based learning. So they can understand the architecture, they can understand the hardware, and they can now build products. If let's say if certain products it doesn't need all the features of an architecture, it needs only A, B, C, D, E features. That can be already customized. That can be customized as a part of the hardware, and your hardware becomes smaller and much more compact compared to your application. So it's called application-specific ICs. You can actually build application-specific ICs that is doing only the job. Let's say that's doing only the job of this mic reception. That is possible with the RISC-V, and you can see what is there inside the architecture. That freedom is possible with the RISC-V. So RISC is it is again reduced instruction set computing, but the 5th generation of RISC, which is now being open sourced for the community. So that's the reason to choose RISC-V.
Okay, so naturally for open source EDA and education, RISC becomes
mostly for education.
As a software engineer, the way I had sort of looked at RISC earlier was endianness, whether it's a big endian or small endian. When we did networking, those are now sort of hidden by most programming languages. Early on, we sort of had to be aware, and we always did H to N and N to H.
Right.
To say, hey, convert it to host Indianness wherever you are.
Right. That's at the software level. Yes,
Yeah.
that is true. But now I think those are basically pretty much hidden in the compiler, and that's all taken care.
Okay.
Yeah. So yes, that is what exactly what you said. That is how we used to do many years ago. Yeah.
And there was this whole feeling that in general RISC architectures would be more efficient because of this translation not being there.
So,
but
yes.
I kept seeing 386 and others being CISC, or if that's the right way to pronounce it.
Yeah.
Like, what happened there? I thought Spark computers were all on RISC for a long time.
Yes.
Even the earlier Apple, what was that, PowerBook were all RISC. What happened there, and is the world going back to RISC, or both are going to stay?
So a little bit of if I want to explain the plain language, CISC is complex instruction set computing. The width is not fixed. The width of the instructions they are not fixed. They keep varying.
These are assembly instructions.
Which finally, so the way your computer networks actually work, you write a program, and that program actually gets converted to assembly instructions. And in the CISC architecture, the assembly instructions are varying width. They are not fixed width. RISC gives you a fixed width of instruction size. Now, the reason since it's varying width, the hardware becomes more complex. More the complex the hardware, more power consumption. It impacts performance will be faster in case of CISC, and in case of RISC, since it's fixed width, your hardware is fixed, but you reduce the amount of hardware, so power consumption is less. So all your mobile hardwares, IoTs, and all these devices, most of them run on CISC because you have to consume low power. You can actually sacrifice a little bit of performance, but they have to run on batteries. Whereas the desktops, what you see as a part of the laptops that we have at our homes, those you will see the architecture which are CISC architecture, because they are powered by the main power supply 230 volts. So there is not much of
that's a good way to look at it. So all the variables would gravitate towards RISC because of power, even though performance is better in CISC.
Depends on application. So for IoT kind of applications, better to have a kind of a RISC architecture which has got fixed width. So the hardware is predefined. We know how the performance power will be, and all the devices which are running on AC volts, on AC power supply, most of them tend to be on CISC because of performance.
I never thought of this part.
This is one of the way to look at it, and there are other ways. There is a whole technical specs behind that. So it's all depends on your end application. So this is running right now. If it is running on 230 volts AC, we'll prefer a CISC kind of architecture for this.
The mic.
I mean, just the electronics behind the mic. So you'll prefer a CISC kind of architecture for this one. But for IoTs, or for the one which runs on battery specifically, mostly they have to be low power. So you go for a better RISC kind of architecture. One of the specs.
So all the we are just discussing those electric scooters, they will use
and applications. If it is on batteries, if it is on huge batteries, like these runs on those small cells. So low power is preferred over here. For the EVs and all, they have big batteries, so they use a mix of both. So it all depends on what the end application is going to be.
All right. And if somebody has to sort of start learning new today, have colleges now aligned their curriculum to what the industry needs, or just like software? I still see, when I talk to people 10 years ago versus when I talk to people now, even if colleges have not fixed the curriculum, and some colleges have done a good job, students themselves, the communities, have sort of figured out that, hey, this is the right way to learn. In some cases, they are actually building stuff. They are becoming product engineers. In some cases, they are just choosing to say, hey, the companies ask us DSA, so let's just learn data structure algorithms, and irrespective of what the college is teaching, they would do well there so that they can get selected, and they can get they can then learn being a product engineer later. What's the scene in the hardware industry? How is college curriculum versus what industry needs? How far away it is from where you started like 12, 13 years ago?
So if you look into the BTech curriculum, they're actually not that bad, because I learned from the same curriculum. And what I see now is whatever, for example, I'll give an example of there was a subject called as numerical techniques, Fourier transform, Fourier series, all those, and we use that concepts right now for building waveforms for our systems on semiconductor system. So if I go back,
semiconductors also use. I'm assuming you would do fast Fourier for.
No, I'm giving one of the example, DSP, for example, signal processing. So you can actually build a signal processing hardware using the concepts which you learned in your BTech. So BTech or B engineering syllabus, that is not bad. I mean, that is still the thing that is missing is how do you basically connect all the 4 years of curriculum. So there are still gaps in the B curriculum. So when I go to a lot of colleges within university, there are some subjects which can be, you can stay away by not doing that subject. That's also fine. But there are some core subjects which is there in the in the B curriculum which needs to be there as a part of semiconductors also, because semiconductors uses almost all the topics that you have learnt in your B. There should be one additional elective. I mean, what we did at so I was an adjunct faculty at IIT Bangalore. So there, what we did was we didn't change the curriculum over there. We kept what they had. We introduced an additional subject, ASIC. It was called as ASIC design, application specific IC design. In that particular curriculum, they had to use whatever they have learned till now as a part of B and BTech, and the program was designed in such a way that at the end of the day you have to manufacture a chip. That's the idea.
Oh, and that's a BTech.
That was one of the subjects in the curriculum that we introduced over there, and the results were very, very good. We saw close to 37 chips getting designed just from that particular course that we did at IIT Bangalore, and that curriculum worked because of the programs that they had already in their entire system. So the entire system, whatever they have done, it is being split into multiple subjects, let's say mathematics, probability, and all of it. But a mixture of all of them needs to be done when you design a actually hardware system, because hardware system has got everything. It has got PCB layout, it has got materials. So when we design our own PCBs, we need to understand routing, CAD tools, all of it. So it has got resistors, capacitors. We have to get the right value of the resistors to make sure you don't burn out your LEDs. So these concepts are already there in your BTech. So the curriculum is it's all there. One
appreciation for the curriculum can be built by a program
by a program like this. That's what we have done.
Project-based learning that is very popular.
Yes. Yeah. So that has actually helped us very well to enter into the colleges, because colleges are doing good, and this was like a cherry on a cake, which is more on a hardware side. That is, so curriculum is not bad. It is in the right phase. Few tweaks here and there, and it would be what the industry actually needs.
All right. Yeah. Okay. And what is the most unique sort of application specific IC or chip that you have seen your students design?
Yeah. So let's say you have many. There is a board, a very popular board, Arduino board or Raspberry Pi board or all of these boards. So there is a program. I mean, there is in this kind of chips that we build, you can actually replicate the entire Arduino chip using this kind of program. So
Arduino,
from scratch. Yeah. So that is one of the advantages of this program. But yeah, it takes time, like 4 months to run the program, 4 months to manufacture the chip, and 2 months to get the chips back and test it. So it takes about 10 months of time. It takes that much amount of time. But to start with, we have done a chip which is very close to what Arduino does. But the cost of the entire system will not be as cheap as what Arduino give, because Arduino gives the boards at very low price. That cannot be done right now, but over the years of time, there we'll see times where this kind of chips are coming up, which will kind of look like an Arduino kind of board, but every student will have their own personal Arduino board, where the chips and the board are being done by the student itself. So that kind of flexibility will be available it's already there, but the price point at which it is available, that's a little bit pricey. So we are all working towards getting that price down. But yeah, there will be a time when ordinary kind of chips or boards can be built entirely from scratch by the participants.
Right. And when you talk about VLSI, this is very large scale. And from layman's point of view, we learned semiconductors or transistors and diodes in school, and then we said, okay, now these diodes can become integrated chips. I've tried to play around with that 555, the very popular one, right? And then people said, oh, now thousands of transistors, it becomes an IC or system on chip or something SoC. This very large scale, how large is the very large scale?
So there was a project with one of the top companies which I was working when I was in my job. So they are able to put about I think 5 million transistors on a single chip, 5 million transistors on a single chip. And the transistors which we learn in colleges, which is the BJT, so that's a bipolar junction transistors which we still use as a part of our board design, and that could also be built as a part of an IC. But the more popular technology that came after BJT it was called as metal oxide semiconductor field effect transistors. It's called as MOSFETs. So
only heard MOSFETs.
So MOSFET is the one that is right now in almost all the devices that you see over here because of its characteristics, low power and high performance kind of characteristics.
They also are the PNP and
they have
both the characteristics are there.
They have
what we learned earlier was the old way to make transistors.
Old way to make transistors, Okay. So the MOSFETs, they have the characteristics of a PN junction diode. So you can there are ways to electrically connect the transistors in such a way that you can make it as a diode. You can make them work as a capacitor. You can do all of this. So once you pack all of them, so if you pack a network of millions of transistors, becomes a real SoC or ASIC design. So at the superficial level, we call it as a system on chip or application specific ICs. But at the core of it, it's an arrangement of transistors electrically connected in such a way that it does a job which it is supposed to do.
Right.
So for example,
and registers are registers.
Registers are built again of using transistors. So you have you have D flip flops. So the way it works is you have D flip flops or registers which are built of logic gates, AND gate, OR gate, flip flops. So AND gate, OR gate are again built using transistors. So we use transistors, and this MOSFETs are basically used to build the gates, and the gates are basically used to build the flip flops. So at the bottom of it, it's all transistors. So the reason our company became very popular is because we understood transistors very well, because the background was manufacturing. When you go to physics and mathematics, which is the core or heart of the entire ASIC design, so that basically gives you the control and the power to think in a much more broader way that how does chips will actually function once you fine tune the characteristics at the bottom level. So we had the control at the bottom level. The moment you change something over there, by the way, there was actually a special curriculum at IIT Bombay where you had a system, you had a chip, but you had to derive all the properties or design all the properties of the chip by just modifying the transistors. So you play with the transistors, you build your own transistors, you build your own characteristics, and use that to model the entire chip. So because of that background, the company actually became popular because we can control the entire stack. So this part is somewhere I feel it's missing. The physics part and the mathematics part that needs to be a part of the current curriculum. That is somewhere it is missing, but it will come as a part of these additional programs.
Got it. And you just said capacitor. I've sort of, since I played around with the 555, so the flip flops there. But I didn't know capacitors are also simulated with transistors now. I use those round ones when
those
I
are
tried.
Also
and we measure those capacities in picofarads.
Yes.
They're not even What are those capacities now?
So we still use those capacitors as a part of board design. So on the boards, we need some decoupling capacitors to build the entire board. Those are still there, but in your chips, we also need some special capacitors. So there is something called as filters. You need LC filters or RC filters kind of thing. So those resistors and capacitors.
High frequency filter, low band filters, or different.
It depends on your application. So for a smartwatch smartwatches, it will be a high performance filter. For it depends on your clock frequency. So we must have seen data sheets which says that it's a 1 gigahertz processor, it's a 100 megahertz processor. So based on that number, you decide the kind of, or design the kind of filters that you need. So for that you need capacitors, and those capacitors we can design using all this using transistors.
So different type of capacitors.
Different types of capacitors, yeah. But the one which you are referring to, that also still we use for board design. So whatever.
Show me your board once. Let's see.
So you can
have two of them here.
Yeah. So
this is community developed board.
This is all community developed board. Yeah.
What is silicon proven training?
So in our field in semiconductors, so there is a slight difference in the software and the hardware field, and that's the prime reason why hardware is. They say hardware is hard, and there is a reason for that, because let's say
software is also hard. But
software is also hard, yeah. But I'll tell you the exact reason. Let's say if there's a software bug, if you have a bug in a software, you can actually fix them through patches. You can send patches, and that's kind of a 1 month of work, or maybe 1.5 months or 2 months maximum amount of work, or let's say 3 months maximum amount of work. In hardware,
we had a discussion about faulty equipment and how does software fix it.
Yeah.
The bit flip discussion that
right, exactly, yeah. So maximum it will go to 2.5 to 3 months of software fixes. In case of the chip that we are actually designing, let's say if the chip is if there is some problem, we take 4 months to design the chip. We take another 4 months to manufacture the chip, and we take another 2 months to test the chip. So that's a total of 10 months of cycle. If there is even one wire, let's say the wires are very thin, if there is some wire which is not transmitting current, that chip is no more useful to me. I have to just throw away the chip and I have to start again 10 months of cycle. So our cycle is 10 months, and compared to software cycle, which is 2 or 3 months. That's why we say that the hardware is hard, because we have to design the chip from scratch. We cannot actually use the chip anymore. It's all done. In a software, even if for 3 months you found out a bug, you will take another 3 months to, let's say another 1 month to deploy another patch. You can take another month to deploy version 3, version 4, version 5. But in our case, the version 1 itself will take about 10 months. Version 2 will take another 10 months. So it goes to years. And that's why when there are comments made saying that hardware is hard, this is the reason that you need to have a lot of patience to actually make the chip function correctly at the first instant, and that's very rare. There are minor bugs which can be taken care, but it has to be accurate to the last nanometer or nanosecond level. So that's where it comes. That's where the phrase comes that hardware is hard.
Now, what's the difference between the VSD Squadron Pro and VSD Squadron?
So
and there is one that is that's where my chip design ends. There is one that is rectangle and another that is square.
So the one which you see on the blue board,
and we'll flash it.
That is the community driven. It is the one which is built by the entire community. I mean the students actually have built the projects on the blue one. So the blue one runs. That's a B-type cable where you can just connect it and you can program it. And if you see, there are small tiny capacitors on the board also.
Are these capacitors?
There are LEDs, there are capacitors, there are small resistors that we use for designing the board.
Is this?
That's the chip.
The main chip.
That's the main chip.
What are these extra
So
chips?
these are peripheral chips. So if you want to program that main chip, which is designed by as a part of the curriculum, you need some USB drivers, you need some memories and all of it. So that is the one that actually helps us to drive the main chip.
So when you are talking about chip design, in a way you are talking about that processor or controller, and not about say how do you design a memory chip.
Today I'm talking about a SoC, like a system on chip. But memory is also a kind of chips. There are categories of chips. So memory is a category of chip. Flash memories are one of the categories of chip. So this one, the one which was built by students, this is basically a basic microcontroller like an Arduino 885 or 886 microcontroller.
Similar instructions.
Not similar. Those are x86 or Intel architecture. This is a RISC-V.
So you need a compiler that.
I need a separate compiler to compile these chips and to program these chips. That is the blue board.
And the red yellow and
so the
white ones.
black board is dedicated for applications who want to run edge AI applications. So
Okay.
anyone who wants to learn about edge AI from the hardware and so by the way, edge AI has got a lot of demand right now in the market, and industry is looking for candidates who can build edge AI applications on hardware. So software side we have taken care. Software has been very well taken care, but they need people who can run edge AI on hardware. So the blackboard is specifically designed for, or it basically caters to that kind of market who wants to enter into the edge AI domain.
Okay. Do you plan to leave like the ed tech part and tech, education part and start doing?
It is already we are a part of we are doing it at the back end. At the front end, it looks the company looks an edtech company, but the back end we do a lot of research. We do a lot of research in the edge AI.
Okay.
The red one is totally made in India. The chips are from CDAC Trivandrum. So they have used 100 megahertz design, and the board is being designed by us. And if anybody wants to run applications like energy meter or electric vehicles, so that is the board to go about.
Oh, okay.
Then
so this is also manufactured in India fully?
India right now, there is only one plant in India that manufactures chips, that is in Mohali, SCL. And other than that, there are plans which is going on within India to build fabs. But right now, these chips...
all the design that you do is all fabless design.
Fabless designs, exactly.
I've only heard the terms from
So that's the so the red one is being that design.
That's why the 4 months it
takes
goes.
to
So if it starts happening in India, your 4 months can be compressed to a month.
So that cycle will still be 4 months because it's mostly because the physical setup. You need the entire physical setup to run. But only I'll save a lot of money on the taxes, on the tax that I pay, or the duties that I pay. That kind of is something that will save some money on, and that is good if you. So we do in bulk. So the variable, the tax part, that comes to hit you once you do things in bulk. So that is where we plan to and plus security. So the chips right now which will be made in India, you will have better control on the entire stack, because we don't know what the other manufacturing. So for example, there is a lot of global
if somebody
challenges.
added a small chip while in your design, you would not know.
No, it is not very much possible with the chips that we build, but there is a lot of threat. Right now where we are talking about a lot of threats, a lot of securities that we want to keep everything within our country's the boundaries. And the reason for that is the security challenge, because if I want to explain you in a technical way, so let's say a RISC-V, we have got this assembly instructions. So if you look into instruction size, let's say 32 bits, we have this bytes.
That much I understand.
You understand, yeah. So let's say if the instruction size is, let's say, 32 bits, for example, and maximum with the 32 bits we can have at most amount of 2 to the power 32 number of instructions. That is a huge space. But in case of RISC-V or any architecture, the amount of instructions that you have is 50, 60 or maximum 100 instructions that you have. So out of the entire space 2 to the power 32, we have so many space, out of which only 100 spaces are being used to store the instructions. But what of the rest of us? The rest of the is still empty. And how will they behave? How will the rest of the space behave? We don't know yet. I mean, there is that's where the security part actually comes into picture. So let's say
so there is a huge security verification that happens.
It happens. Yeah. There are a lot of verification things that we run on our chips and all to see whether it is compliant to the current instruction set. But anything can go wrong in that particular space, and that's where the hardware security comes into picture. And we will have better control over that particular programming space if the chips are built in India and we have control over the entire stack rather than getting chips from outside. So that is one of the major reasons we are actually building a Fabs in India, so to have the entire control of these.
If there were Fabs in India, I would not be doing what you're doing.
We will have control over it. We'll know.
You personally will probably be part of a Fab and not part of the ASIC world.
Yeah, exactly. Yeah, I would be part of the fab, because that's the field which I love the most. And secondly, the control over the entire when I design a chip, I should be know that it is completely secure. It should not put some something which the chip is not supposed to do. So we know what the chip is supposed to do. That is clearly defined in the specs. But the way security area works is the chip will do or function things which is not supposed to do.
Yeah.
So how do we basically control that? Fab is one of the major targets where we can control the whole thing. That's why we are trying to see if everything can be built within India.
There is a GitHub repository called Big List of Naughty Strings. I don't know.
Yeah.
So what it does is, for a software, you can use these as inputs to say, does your software break? Because you are probably only trying to test for your inputs. You're probably trying to test for some boundary conditions.
Yes.
But as you said, software, the security issues would happen with instructions that are empty. You don't know what is there.
Yeah.
And is there an equivalent of this big list of naughty strings for hardware?
So there are tools. There is one tool called as chip whisperer.
Okay.
So we can actually inject some faults in the chip, and we'll try to create a software way to secure the chip. So that is still available.
Okay.
But that is again on the software side. What we are looking forward with all the fabs that are coming over here in India is we are looking from a security standpoint, from the manufacturing standpoint. That's again one space which is kept open.
Right. I opened the next one that you said is for school kids.
Yeah, this is basically So right now
is that a mic?
That is a buzzer. That is a buzzer. And you have the push from
these are called 7 segments. I didn't know that.
These are 7 segment LEDs. Yeah, there are
I knew there are LEDs. I just didn't know they're called 7 segments, and makes sense why they're called 7 segments.
Right. So this is there are 2 7 segments. There are push buttons. There are some push buttons. There are some dip switches over here, and there is a OLED. So what this particular thing enables?
Oh, this is a baby OLED.
There is an OLED, This is OLED.
Okay, I didn't know it could come in small size.
It can, too. And there is a servo motor.
Yeah.
This is the servo motor. Yeah. So now
I was wondering if this will actually rotate. Looks like it will.
Yeah, you power it on, and it will run the whole system. So now
why is this? Sorry, I'm just interrupting you. Why is this part slightly elevated?
It is
the chips. It was not elevated.
Yeah. So these are called as development boards. This is called as a training kit. If you want to train somebody, that's why it is mostly for the to showcase what board are.
Trainer kit.
It's called as a trainer kit. Yeah. So trainer kit generally applies to those terms where you have a board already, which is this one. It is then a board, and that will have multiple interfaces, peripherals to control this one. So that's why you have all this extra peripherals that will be controlled by this particular board.
Okay.
So the way we do it is we train school kids from 7th to 12th on this trainer kit, and the reason for that is we want to encourage them more towards hardware. So what is happening is there are a lot of software-based curriculums.
This is online. Sorry, I'm again interrupting. This is an online program?
It is an online program, and the kits are being shipped to their homes.
Okay. How does one register, man?
And
you said this is free.
It is mostly
covers.
Yeah, so some or the other companies, we do it as a CSR program under CSR program, and that's why it goes as free of cost for the students. And so they have to just register, but there is a strict process on how do the top 50 or 100 students get these kits. So there is a process, and we have to go through that process. But nevertheless, the top 100 kids or top 150 kids, as decided by the criteria of the CSR bodies, they decide on who are going to get them. They have to go through this entire program. So many school kids register.
But can I just do this with you if I am a college?
You have to purchase the kit. Either you purchase it from our website, or you have to you go through this program, which is more stringent. Either ways it's possible.
Yeah.
So this is mostly to promote school kids to enter into hardware. So right now we have seen 8th standard, 9th standard, 10th, 11th, 12th. They are mostly inclined of a lot of software. They do CAD tools and all of it. And we want to change the trend where they enter and start getting excited about semiconductors, because the demand for semiconductor engineers is going to rapidly increase by 2030, 2032.
I can imagine.
Yeah. And we need a different kind of engineers. We don't need the regular ones who go through the regular programs. We need we need a different mindset kind of engineers, and that's where these specialized kits are being designed to cater to the engineers whom we want at 2030, 2032. So
I need to come to your floor and learn more chip design so that I can become the different type of engineer. They'll succeed. No, software is here to stay.
No, software engineer is there because we need. There is a different kind of software engineers that we need, and we don't need people who understand syntax semantics, because that's not taken care by the AI part. We need more of analytics side, the one who can design the software. That kind of people are something right now is needed. I mean, specifically like people like you is what industry right now needs.
Yeah, that brings me to the next one that I'm curious about. And there is a question that I usually ask all my guests. What does their day look like at your company? And I'm just going to skip it maybe.
Okay.
Since you mentioned software programming, I keep hearing FPGA, which has programming in it.
Yes.
And these are, you said, also FPGA kits.
Yeah.
What's the programming part? And is that software? Is that not software?
So it is called. So there is the word is called as. We use a different kind of language. It's called hardware description language.
Okay.
It's called HDL.
Okay.
And the way software guys use C, C++, that's a software programming language.
I remember people use this software called Keel. That was HDL?
That is that's for a different purpose. For the chip design, we use it's called Verilog. In our case, it's called Verilog or VHDL.
HDL.
HDL. So it's called hardware description language.
Okay.
So Verilog is a language that we built our chips on, and these kids, the students whom we work with, they start from the voltage and currents. They start from voltage and currents, and from there they are slowly they go towards the HDL kind of language.
Good.
And they use that language to program this particular kit.
Do they need to understand, and should they be able to read a register when they see it?
That's a part
I
of
have forgotten that skill.
So that is a part of the curriculum.
And I remember there was a Kirchhoff's law. We did so many equations.
Yes. So
you also teach that?
Yeah. So the reason
those are basics.
Yes. So the reason we start from voltage and currents and then move them closely to VLSI is to bring out that culture that the whole, we also fall under the electrical domain. So we are not separate from electrical. So the moment, let's say if anybody is asking that what skills do we need for to get into VLSI and all, and AI is changing this and that. So the fundamentally your resistors, capacitors, RC network, your voltage, current, Kirchhoff's law, and all those, if you are good with those fundamentals, you can the programming part is something which you can derive from this concepts. So anybody who is good with core fundamental resistor, capacitor, current, voltage, these fundamentals, we guide them from that point to Verilog to make the to make an understanding very clear that the moment you're good with these topics, VLSI Verilog is something which you can easily move into. But make sure you're good with physics, current, voltage, and all these things. So
when I talk to software CTOs, they tell me the same thing, that you have learned framework like React or Angular, but do you know native JavaScript? Vanilla JavaScript? If you don't, then it'll be a problem.
Right.
Very similar. I have a lot of software related questions because a lot of software engineers and engineering students see this podcast. So for a software engineer, what's the simplest mental model for chip design? Like if you can use software analogy, otherwise I can convert to software.
So you want a model for them to
understand chip design. Somebody who does not really know hardware chip design, but you want to explain that term. They maybe understand programming. They understand logic. They understand if else, loops. Right.
Okay. So the way if you want to explain a chip design to a software engineer. So you have all these applications. You have Zoom, Netflix, and all this. These are at the application level. So the moment you run, you hit the that button to open up the application, you see things happening in milliseconds. You click on it and the Netflix actually just opens in your this thing.
I wish you would use my company's name, but it's okay.
Oh, okay. So any application. So the what happens, what goes behind that is that particular application gets converted into. I'm speaking in a very layman language, that that particular software or application gets converted into assembly languages. There is a compiler in between that converts the whole thing into assembly languages. So in our software engineering, we learn add instruction, add, subtract, load, store, those kind of instructions. So your application gets converted to that kind of language, which is understood by somebody who understands hardware and the upper layer. Internally, there is something called as assembler. Once you compile, so all the applications are nothing but programs. They are at the end of that, there are some Java programs or C programs, some programs. So that high-level program is getting converted or compiled to a mid-level assembly language program, which has got add, subtract instructions. This add, subtract instructions and whatever instructions, that is basically specific to one particular architecture. So for RISC-V it will be different, for CISC it will be different, for other proprietary architecture it will be different. Everybody has got their own assembly languages. The next what happens is, from the assembly language you have something called as assembler. So from there it converts to assembler. Now what does assembler does? Assembler converts your instructions to bits, binary patterns. So 1010, all of it. It basically creates a stream of bits. Now when this stream of bits enters into your chip input pins, it basically, for example, there's a start bit. It takes all the binary patterns. There's a stop bit. When the chip actually takes this stream of bits, it understands what it is supposed to do. So if it gets a add, let's say if it gets a instruction, a binary bits which corresponds to the add instructions. So the CPU understands that it has to add something. If it gets a binary pattern which is subtract instruction, that CPU understands that this binary pattern refers to, I have to do a subtraction over here.
So add instruction is change of voltage on part of the pins.
So in our case, I'm talking about registers. You have to add it to registers and store the value in the third register.
Oh, the register is a real register.
It's a real register. 8-bit registers or something. So the CPU understands that I want to add 2 registers and store it over here. So this complex high-level applications are nothing but a series of this assembly languages, and these assembly languages are converted to ones and zeros and given to the CPU, and then CPU understands what it has to do, and it does that and it sends back, and that's where you see the Netflix or any application being opened the way it is supposed to open. How fast this happens, that is decided by a CPU speed. So when you talk about 1 gigahertz speed, 2 gigahertz speed, so old generation phones or there was this big computers. It was not as sleek as this one. The computers they had got this tubes
big boxes.
Boxes, So those boxes used to take at least 1 second to open one application. Now we take less than a millisecond to open that application, and the reason is that reason comes back to the transistors that we were talking about. So transistors sizes have basically shrinked. Initially, you can think of this, that the transistors were this big, and now the transistors are very small. So the time
were this big. I mean, they started this.
The
first transistors that I used.
I mean, from if you zoom in and look into from a lens point of view, under the lens, the transistor will look this big, and the current transistors will look very small.
Oh, even
under a microscope. So we use a technique called as electron beam lithography. It's a lithography technique, so it's a technique where we can view these transistors. So you can think of it in this way, that the time for the current, if you used to take certain time for the current, let's say T, now it is taking T by 100. It is so fast.
This is where your nanometer.
This is where nanotechnology, nanometer comes into picture. So initially it was 1 micrometer big, and now we are at 7 nanometers or 2 nanometers in that scale. So that's how you can relate. And
so
all
your degree of nano.
My degree is nanotechnology. Yes. So that's how the software engineers, they don't see what is happening, but they are writing applications and programs. All they are concerned is that how fast I can get my response, and that fast is decided by the again it comes back to fundamentals, which is the transistors.
So what, I partially got this answer, but what do you wish most software engineers understood about hardware? Like, what's the biggest misconception according to you?
So let's say if I speak to let's say I speak to a software engineer, and the part that got I think in the software computer science curriculum, if there so at least in our curriculum we had a little bit of mechanical, a little bit of applied mechanics, we had a little bit of we had something of everything, and towards the end it was core it was core electronics. Similarly for software, if we add little bit of applied physics, little bit of applied physics, little bit of transistors also is there as a part of the first year or second year, I think things will settle down. It will be easy for us to speak to the software engineers, but currently when I try to explain a software engineer about the entire chip design, I find it a little bit difficult. But the good part is that they understand programming. So we are not doing anything which is different than programming. We also write programs. We also use the loops and all the case statements, but we do it which is more specific to the hardware. We make sure that our code converts to a hardware, compiles to a hardware. In the software case, it has to compile, and it has to make sure that it is compile free. But we go one step ahead, where we have to make sure that it is basically getting compiled to a real hardware, and that real hardware is what we use to build our chips. So that is little bit, but yeah, I think eventually with the amount of data or content that we have globally, it is not very difficult for the software engineers to understand what is happening at the hardware. It all comes down to physics and basics and transistors.
You talked about this compile. What's the equivalent of this compile, run, debug, which is what a lot of software engineers do? They write code, they compile it, they run the code, they find an issue, they debug it, write more code to fix the issue. The first 4 months, not the manufacturing, first 4 months, what does this compile, run, debug loop look like?
So it looks exactly the same. The first month of the entire 4 months is what you just said. Compilation, then debugging, then verifying whether the code works or not. That is exactly
These are chip simulators that you're working with.
There are some simulators which is specific to hardware description language. So you use GCC compilers, maybe for example. We use some standard hardware based compilers that basically compiles and gives us waveforms, and we can take a look at it. But what you do, that is the first month of the entire 4 months of exercise, and the remaining 3 months is all hardware specific work that we actually do. Now, for example, in our case, the constraints or the specifications is more defined towards the hardware side. We define the frequency should be 1 gigahertz, the speed or for example, let's say if I press a button now, and at what time I should get a response, that speed, it's called IO speed. That is something hardware specific constraints are being given by us. In your case, it will be an application specific constraint. So that's the difference. But more or less conceptually, it remains the same. We tend to go more towards AND gate, OR gate, and flip flops, and the software people tends to get more towards the application side. That's the only difference that we see. Else, the first month remains the same.
What do these compilers look like? Like, for example, you said GCC. So there is a compiler, linker, assembler, and there is this whole thing that software engineers use. Are there open source equivalent and paid equivalent for these for the Verilog or HDL world?
Yes. So we also use GCC for the RISC-V compiler. So it's called RISC-V GCC. So the normal GCC that you use is for your machines. We use RISC-V GCC. So that's a compiler for us to see whether So let's say there is a common C program, and when you type GCC, it will give you an output. Let's say sum of 1 to 10. It will give an output. GCC will give an output. We have to make sure that we have to get the same output on RISC-V GCC also. So we do RISC-V GCC and the program, and we get an output, and that basically confirms that your output with a standard processor and output with my RISC-V processor is going to be the same. That's my first level of verification. Like this, there are close to 1,500 verification tests that we run on a normal RISC-V kind of based of processor. That's our first level of test. Whatever you do, we also do at the first level. And then actually the second level of compilation is the hardware compiler. So we build a hardware and we run the same test, sum of 1 to n, for example, run the same test on the hardware. Our output should be the same, exactly what we got with your GC, whatever output you are getting. I should get the same output with my hardware, a new hardware, run the same programs, but the output will be sum of 1 to n.
Okay, so first it was simulator, and now it is a real hardware.
Real hardware, which is not on the chip yet, but on the simulator, still on the simulator.
Oh, it's still on simulator.
And the same, then I have to go through the entire chip design process. I get that, I ship the chip, I get the chips back. I'll take the same program and run it on the board now, on the chip now. I should get the same sum of 1 to n equal to whatever your GCC gave me. I should get the same output. If that matches, then my chip is working fine. But because of, let's say, 1 bit change here, or 1 wire, or there was 1 dust particle.
Which it could be a manufacturing.
It could be a manufacturing defect. Yeah. Okay. If it is a manufacturing defect, or if it is something which is not under our control, let's say some voltage spike came and hit one of the pins of the chip, and sum of 1 to n, I'm not getting the sum of 1 to n on my chip. I have to just throw away the chip, and I have to build a new chip. So that's why the cycle over here that you see over here, it's more than 8 to 9 months compared to a software cycle.
Got it. What's the equivalent of a performance profiler? We talked about this latency or throughput. What's the equivalent there, and how is the performance tested? So far, this felt like functional testing.
Functional testing, exactly. Yeah, this is functional testing.
I also sort of could map these stages to dev testing, pre-prod testing, and maybe a post-release testing or something of that kind.
Yes.
What's the equivalent of performance testing for chips?
Yeah. So in very simple terms, we check whether how fast I'm getting the response. So am I getting a response after 1 second or 1 millisecond, or that is my first level of basic performance.
But that's
testing.
Better done on the real hardware than on the
real hardware, not on simulator, on the real hardware. Finally, once we get on a simulator, there are tools which tells you that at the end of the day your chip is going to estimatedly it is going to run at so under certain voltage temperature conditions, under some conditions. Same chip, let's say, will give me 100 megahertz in over here, and the same chip will give me let's say 80 megahertz in some desert area. And the same chip will give me a better frequency in Iceland, or
this just increased distance or something else too.
So we change the conditions around that particular chip. We simulate that as a part of this thing. So we make sure that we simulate it within certain range, so that chip is functionally working at least in the room temperature. So that kind of testing is something which we do at the simulation level. And once the chip is back, and once it runs on a real board, that frequency is now fixed. I know that it is very much predictable that my performance will be somewhere between 80 megahertz to 120 megahertz. So that is very much now I can predict because of the kind of simulations that I do before even sending the chips to manufacturing. So that's what we do. So that's where we say that the hardware is hard, because we are trying to simulate across conditions and a bug.
Temperature conditions I didn't think of.
Temperature conditions, voltage conditions, process conditions. So a transistor also. So let's say there are 2 transistors are not same on the same wafer. It's something called a silicon wafer. We manufacture all our chips on a piece of wafer. So the same transistors built using same conditions will be different on the same silicon wafer. So that's basically called as the process variation. So because the gases that we put to build the transistors, or that gases amount might be, you can think of it like you cook a chapati. The taste is never the same today and tomorrow because of the amount of gases. There will be slight changes in the number of gases. Same happens with us also. That's called as a process variation. So because of that process variations, we have to simulate that as well. Simulation for us takes huge time, and that's another constraint that that hardware engineers face, because we need huge compute, we need huge RAM, CPU, and all of it to simulate a certain condition for a chip. Now, for example, these things can be simulated under a 32 GB RAM and 320 GB hard disk, and something about 8 core CPU. I can simulate all of them. It is enough for them, just enough. But imagine you're building a GPU, that kind of thing where the AI actually is running. So to simulate that kind of chips, that kind of conditions, you need bigger systems. You need bigger. That's where all the servers market is coming into picture. You see a lot of investment going into server market because, or the GPU market, because you need to compute. You need to run those kind of computations on a much more 1000x higher scale than what we are running as an education program. So that's where the compute part actually comes into picture.
Very, very interesting. So in order to build larger chips, you first need the large chip to simulate.
Yeah. That's where most of the funding actually goes. You have to get the servers right.
What's the equivalent of tech debt for hardware world? I don't know if that term exists in hardware.
Tech debt.
Yeah, tech debt. So we take technical debt. We say, instead of doing the right way to design this, because that'll take 2 months. We only have 2 weeks to ship this. Let's create a hack. Let's fix, do it this way.
Okay.
Are there such shortcuts taken on hardware at all?
Hardware, the only sacrifice that you can make is you can lower down your frequency, but that's the best you can do. There are so in our case, if a chip fails, we have to just throw it away. I mean, that's the only thing that we can do. That's why the patches, it has to be, the second version has to be right. But there is a way. So before even manufacturing the chip, we make sure that the chip actually works on a FPGA world. So the reason we have FPGAs is because you can build a prototype of that entire system, and test it on a real FPGA board. So you do that, at least you're 90% sure that, or at least 99% sure that your functionality is retained. And the other problems that might come is because of the chip design flow, which is actually happening at the back end side, and manufacturing side. But functionality wide, I can say that my Verilog program is functionally correct because it has been verified on an FPGA board. That is the best, and that cycle is still it is still a month. It's still a month cycle to do the whole thing on an FPGA if it has been a very bigger or large system. That's the best we can do. Otherwise, if a silicon is dead, it is dead. There's no way to revive it back.
Got it. What's the, let's say a software engineer wants to, after hearing all of this, they still want to move to the semiconductor industry. So what's the best role for them? Like some validation, testing? I hear similar terms. Where do most people start? What's a good way?
So hardcore, if he wants to enter into hardcore semiconductors, as I said, I mean, that's true for all the engineers. The fundamentals of RC, resistors, capacitors, current, voltage, physics and mathematics. These are some of the fundamental core topics which he or she has to go through it. Because the other things, the other technologies could be learned once you are good with fundamental. Once you know what to do, once you ask the right kind of questions, the other technologies could be learned. But all of these high-end fundamental high-end technologies, they are all, at least in our case, VLSI and nanotechnology, they still are under the electrical branch. So electrical has got control systems, it has got VLSI, it has got embedded, it has got power engineering, but the main mother branch is all electrical. So the moment you get control of the electrical thing, I think choosing any of these 4 fields will not be a tough task for a software engineer, but the core thing is electrical. There is a lot of things. So as you said, there are Kirchhoff's law, voltage law, and all this Ohm's law, all these kinds of laws. Beyond that, you have RC circuits, and in reality, a transistor is nothing but a pure RC circuit. If you look into a MOSFET, for example, that's also can be modeled as a resistor capacitor. So the moment you get control over these topics, the other things are already taken care. You can learn them, using some tutorials or some course. You can actually learn the other things. But these are things which lies in the heart of semiconductors if you want to go long term. So semiconductors and software, there is the bigger motivation why students are right now preferring semiconductors, because the initial growth is a little bit slow, because you need at least 2 years. You need to spend 2 years in the industry to get a hold of what semiconductors and hardware is. But eventually you grow a lot. Eventually it's an exponential growth. For a software, at least what I see is initially the growth is very high, like pure software engineers. But at some point of time, there is a lot of repetitive tasks which is now being taken up by AI. So the amount of innovation that is available, innovation opportunities that is available with semiconductors and hardware, that is right now is going to explode. And typical package wise, for example, right now, just 3 weeks back, we had 5 to 6 participants who got placed in semiconductor company. Typical packages for a BTech, it start if you're good with fundamentals and done the 1 year of or 1.5 year of training. Typically, it starts with 25 lakhs per annum. It goes till 33 lakhs to 35 lakhs per annum for a fresher. For a fresher, when I say fresher, he's not a fresher from in semiconductors, but he has done all of it. He has done the 2 years of hard work, and after that, it could be an MTech program, it could be a program, or he could self-learn, because we all in our case, we did self-learning. We didn't go to any institutes to learn semiconductors, but we spent 2 to 3 years in the domain, and then our starting packages comes to around 20 to 32 lakhs in that case. So and it grows. 15 years or 16 years of experience, it actually grows with stock options, and there is a lot of new things you can do.
I'll come to you for funding.
Yeah, no. So there is a lot of things you can do after 15 years. There is always growth. And software, I don't know, because I haven't interacted much with the software counterparts, but I think the software engineers might be able to tell their growth scale at the end of 15 or 16 years. But
we'll discuss that off the camera.
Yes.
So we briefly discussed, but what are your thoughts on India's role on the global semiconductor ecosystem? Where are we right now? Where do you think we should be? Where are we likely to land in next 5 to 10 years?
So I'll speak from my perspective. What I have been seeing, that in fact the semiconductor domain itself, the kind of attention that we as a company are getting post 2021, 2022, when there was announcements about building semiconductor fabs in India, that has gone very huge. I mean, we are seeing a lot of requests, and we are running, the kind of programs that we used to run from 2011 to 2021. That has gone 5x or 10x after 2021, and that has gone. The reason it has increased is because the demand suddenly for the hardware engineers have exponentially increased, and that's where we see a lot of requests coming to us saying that how can you do the same program at large scale? Because initially we used to run for, let's say 40 candidates, 50 candidates, or max 100. Today we run the same programs for 3,000, 3,500 at scale, at first, at the launch. So for example, if I launch a program, we get close to 3,500 participants, and we run at that particular scale for every 3 months. So yearly you can see there are close to 10,000 engineers who are actually building or designing something or the other thing. But the outcome, or the outcome that you see out of this whole 10,000, it's only 0.5%. Let's say for the current program that we are running, a tape out chip design and manufacturing program.
What is tape out?
So tape out is a process where you send the chips to the foundry. You send the design to the foundry for manufacturing. So that for us it's called as a tape out. So
where does it come?
It comes from, so there are, in old days we used to use magnetic tapes to send the chips. Now we use a file. So the file, so that the term has retained over the years. So we call it as a tape out. In simple language, when you have a design ready and you send that design to a foundry, that term is called as a tape out.
Okay.
So we were running a program, very similar program, and out of close to 3,500 participants, there were only 15 who were able to complete the phase 1. So partly could be the reason that there were a lot of drop-offs, because maybe it was not easy. The program, you need to spend at least 10 to 12 hours debugging. There are a lot of parameters that you have to debug in order to complete the phase 1. that could be one of the reasons for the dropout, and you need huge patience to actually cover the entire you need to be constantly on your toes, because things change very fast too in our programs as well. It's as good as a real chip that you're designing for industry. So and that's why this 15 or 16 people who got, or 0.5% who completed the whole thing, they are special, and that's why the packages for these are quite high. So nothing wrong with the other participants pursue their own field. Maybe they after 1 or 2 weeks they might have found that there's something which is there, they might be not interested, they might be interested in something else, which is also fine, but that is the rate at which we are operating right now, and that number has to increase.
That reflects on how India directionally is going towards being a semiconductor nation.
Yeah. And that also is the reason we are running the programs from schools itself, so that that awareness is built from schools, and they know how interesting the hardware design field is, and they continue to pursue that direction, because changing the minds of engineers who are at their third year or fourth year, it's little difficult compared to inculcating the hardware ideas or seeding the hardware ideas in the minds of schools and colleges. So that's the reason that all these kids actually came into picture.
So today the hardware jobs are largely with MNCs. You started with Qualcomm, or there are homegrown Indian large IC design companies now that are able to hire.
There are both. There are in fact we also hire a lot. Our hiring is a little bit of a Gen Z style. So we don't do a full hiring. So we have some projects. In fact, any student who is open to new ideas and whose vision aligns with our vision, we basically do a soft hiring with them. We do a soft project with them. And so right now the hiring is happening across service companies, but the hiring style has changed. They don't need the regular engineers who has done a curriculum or done a program, but it is not inclined with their current project needs. So, for example, when I was going for a semiconductor job, for me, understanding VLSI flow or understanding fundamental, that was enough for me to get a job. Now things have changed. Now you need to know the flow, but on top of that, you need to know how things actually run in the industry, and that is at least, it will take at least you a good amount of 12 months to 15 months of time to understand the whole thing. So industry are open to these kind of candidates who have been doing something. The current trend which we see is that the expectations from most of the freshers is that they have done a program and they are expecting a job right on the third month. But somehow that doesn't get aligned with our industry, because right now this was good in 2010 when I was doing my engineering. But today they need to know the entire system, and it is a little bit of a difficult thing for the freshers as of now. But that's how the industry is. They have to go through the entire flow, at least 10 to 15 months. They need to know not only the technical part, they need to know how things work when put together as a system, and that takes good amount of time. And that's why you see only 20-30 people who go through this flow. But once you have done this, there are service companies, homegrown Indian companies, MNCs, all of them are right now looking at this kind of talent to work with them. But there is a special need right now that they have, the students should be having.
Got it. What are your top 2 tech achievements in VSD?
So the first that was actually that actually helped us to move from. There is a concept called as 0 to 1. You move from 0 to 1, and there is 1 to n. So the one thing that got us from 0 to 1 was the chips. The chips was that actually working, and that chip was one of its kind of a joint collaboration between Google, eFabless, one more company in US, and VSD. That chip actually showed how the whole world actually collaborates to learn things, and that's where that got the attention of the entire world. So when we brought this board in the market, the blue color board, that brought that board in the market, brought the chip, and we made an announcement that this chip was designed by a student, but with the help of all the entire global community. He was not alone. He was helped by so many people. But she was the one. She was one of our students, and she is now in Georgia Institute of Technology. She got admissions, and she's working on neuromorphic computing. But she was the one who arranged the whole thing. She managed the whole. She talked to VSD, Google, eFabless, and made sure that things happen. That's the kind of skill that people are looking for, and that was the first breakthrough that happened for our company. And after that, the events that happened that just followed this one. That was nothing called as a breakthrough for VSD. Apart from the others were just 1 to N. The 0 to 1 is what happened with the blue board. And other achievements was like 1 to N. Like we built, we made sure that a kid, an 8th standard kid, was able to build an entire RISC-V CPU on his own on this particular white color boards. And he was one of those kids who not only completed the program, but he went beyond and built his own system. And completely mentored by our team. And he was the one who built a CPU on the whiteboard. So these are all 1 to N kind of thing. And the breakthrough was the blue board.
Got it. So in edtech industry, the biggest problem is how do you iterate upon the course? You have to sort of iterate upon the course, the curriculum, as well as the board or training kit that you just showed to me.
Right.
How do you go about doing these iterations today?
Yeah, so that's where actually we work a lot with the Gen Zs. That's where Gen Zs actually came into because they are going to so many colleges. They are going to so many universities. They for example, some of our team members, they work with US universities. They are placed over there, and they see things. They see things, and they come back to us saying that this is if it had been in this way, if the board had been this way, then this is something which would have been excited me or my college. I would have loved to learn this thing. And we take a collective response from most of the students across India. Actually, across India, we take all this collective response, and then we have our own board team. So he basically takes up all the requests, and he finds out a common point, and based on that common point, we keep on upgrading our boards. In fact, the blue board wasn't even planned. It wasn't planned that we wanted to build a board and things. It was not planned. Again, there was one of our students who is now is working with is now doing his PhD in Purdue University, US. 3 years ago, when we met him, he pointed out a few things that if he had these things as a part of his program or as a part of his curriculum, it would have worked. So we worked with him, and we said, okay, this is something which we are getting. We are getting the chips, manufactured chips back from the foundry, and these chips are special chips because you can actually see what is there inside the chips. For example, you can see the code or the program that is making this particular chip. So it's completely open source. So we worked with him, and we designed a board and the whole thing around it, and that added up a value. That was a value addition with the existing curriculum. So now, I remember I was talking about you have a C program. It should give the same output with GCC. It should give the same output with RISC-V GCC, and it should give the same output with this one.
Correct.
So that whole program was actually designed to make sure that students understand from software to hardware what actually happens.
Cool.
Second, there was again another student when we were working on doing one of the hackathons. So we do a lot of hackathons across multiple technologies, pan India. We've done close to 10-15 hackathons pan India and global. So one of the participants from there, he said that he wished that he had access to. He had early access to some of the RISC-V development boards already, cheap and cheap early access to RISC-V development boards. That's where the yellow board actually came into picture. So again, our board team took all the inputs, collective inputs from all these students, and that's where the yellow board actually came into existence. There was another hackathon there which we did on the sensors domain. So India is right now building a lot on sensors.
Okay.
So there, somebody said that if the boards had been, if there were boards which had got Bluetooth Wi-Fi capability, they could have done even more things and all. That's where the orange board actually came into picture. Then there was, as and when we are getting requests, we are trying to upgrade the board, and we're trying to keep in pace with the current generation. What exactly is the need for them? So we listen to a lot to the Gen Zs, and they actually help them. They actually teach us what next should be done, because a category of Gen Zs are being replicated all over. If you have, let's say, 100 people vouching for the same idea, there might be 100,000 or more than a million would be asking for the same thing. So that's how we basically keep updating the curriculum. So these goes as a part of the projects, while the fundamental still remains the same. It doesn't change. So fundamental curriculum will still remain the same. And these are on top of, if you want to do projects after you finish this one, you can take up this board. That's how the trainer kit actually came into existence, because one student, this came from one of the 9th standard student. He said that he is the one who built the entire CPU on the white color board. He said that he wished that he had a ready-made kit around the whiteboard that he can play around things. So that's how the board actually came into it. We are keeping up with the Gen Zs.
Very nice. Okay. Kunal, what's something that people would not guess by looking at your LinkedIn and VSD website?
So there's a lot of research that happens currently. As a VSD team, we work on a lot of 10 different projects at the back end, which again, some of them caters to the education market, some of them caters to the some kind of market which we're trying to change. Let's say a certain category of market was using X boards. We want to replicate it by VSD boards. Same cost, same pricing, same performance, nothing changes. That is the kind of shift that we are trying to do. And again, these are all done by students. That you won't see on the website. On the website, you will see only the tech part, which is what we want to show. But something, and again, anybody over here who wants to work on these cutting edge projects, which are specific to semiconductors and RISC-V. So our niche is semiconductors and RISC-V. If anybody is looking to work on those technologies with us, they can of course contact us. But this is something which you'll not see on the website. You have to personally be in touch with us to get to know those projects.
Good. Let's do a quick rapid fire.
Okay.
RISC or CISC?
RISC.
Okay. Fabless or with Fab?
With Fab.
Okay. Biggest tech regret?
None.
Oh really? Oh,
None.
cool.
Yeah.
Most overhyped tech trend?
Most
overhyped tech trend? Everything deserves hype. Cool.
It's working for us. As long as it's working for us, it's fine.
One book every engineer should read.
So there's a book called as 0 to 1. That book actually tells you, let's say if you're a founder, if you're a startup, that what are you exactly doing? Are you trying to replicate one market and doing it in a much more better way, or are you trying to do something new, pretty new?
Yeah.
So that book is called 0 to 1. I recommend everybody every startup founder to read it.
Cool. Okay.
Yeah.
Favorite open source EDA tool?
There is a tool called as it's called Magic.
Oh really?
Name, so it's called Magic.
Good name.
That's a fundamental tool for all the EDA tools that you have over here. So it's called.
Okay. And maybe I already know this answer, but most underrated VLSI concept?
Most
underrated VLSI concept?
Resistors capacitor.
Yeah, that's what I said. Probably you'll know the answer. Okay. Coffee or chai for you?
Coffee.
All right. Cool. Who are your go-to people for learning about VLSI, apart from yourself, of course?
So I was very fortunate to have a good mentor. He is Professor Kamakoti from IIT Madras. When we were at IIT Madras, he was he kind of mentored us for the whole 11 months. And the reason that you see all these boards and all the way the thoughts that are coming up to our company, the culture, ideology, that is all because he mentored us in the right way. And there is one more professor, Professor Madhav Desai from IIT Bombay. The reason we started the company and the initial the way the company should look like, the long-term vision statement. That's Professor Madhav Desai from IT. So these are my, I can call them up anytime and ask for guidance. Yeah.
Very cool.
Yeah.
Kunal, it was fun having you on the podcast.
Okay.
I learnt a lot. I think I'll probably definitely send, not probably, definitely send the kids to see if they can learn chip design from you.
Yeah,
and we'll see where it goes.
Yeah, it was nice talking to you.
Yeah,
Thank you so
Kunal.
much.
Okay.